Although not necessarily used in municipal applications, here's some interesting pump types you should know about. The first one, turbine vane. And basically what happens here is you have a disc with little cavities on it on both sides. And the disc rotates. In this case, if you're looking at the top view, what to us would be counterclockwise. Um, Liquid comes in, water in basically is carried around that passage. Now, what happens if you look at the cutaway in the bottom right-hand corner there, the water is struck by the impeller, which spirals it out, and then it circles around. It's speeded up, of course, so energy is provided, circles around, slows down, picks up pressure, and then hits again, comes around, same thing. So it actually does a collection of these loops as it turns around, and each time it's caught by the impeller, the speed is increased, and each time it's diffused, the pressure is increased. So you end up almost like a multi-stage pump. Um, the nice thing about these things, they're relatively low capacity pumps, but very steep head curves. Um, Classic application is boiler feed, and the only downside is the fact that between the suction, the inlet, and discharge is a very short distance, and that is serving as the pressure break between the two. So as that wears, the pump starts to leak. So generally they are oversized because they do tend to fall off in terms of capacity with time. But there they are. Um, an ejector is a pump that isn't. Basically, if you have high pressure coming into an ejector, as you can see in the view, that creates a drop in pressure because it's pushing fluid down, which draws fluid in. So essentially, it acts like a pump. You have water coming in, but it'll move much more water through the suction and discharge. Okay, um, seen in particularly in well pumps, non-submersible well pumps. Also good for handling hot condensate because cavitation on non-issue. And you can actually use city water pressure and create a little sump pump. Turn the water on, it plays pump. Now, taking that ejector a step further, uh, domestic well pumps, and these were really big prior to the days of submersibles and still are found around today. The most common variation of it is the the combination pump. Okay, and basically what it has is a venturi on the inlet, but the inlet is removable. So when the inlet is bolted to uh, the pump has a little throttling valve on it that basically allows the pump, and you have to prime it, have to fill it with water, that basically will allow it to pick up pressure, and it goes around through the inlet venturi, and that draws water up from below because that venturi, as I say, is playing like a pump. Now, it's limited to a lift of about 25-foot maximum, and there's a couple of ways of installing them, uh, either in a well, foot case, all this stuff, or with a well, sand point, which is really not so much the pump issue. But basically with that, there's a single pipe. Now, these things are also convertible. That inlet venturi can be unbolted and put down in the well with two pumps, one with pressure going down, the smaller of the two, and one coming back with the water that it is effectively pumped. And again, they mentioned the control valve on this thing to throttle so you get some back pressure going. Okay. Um, Located in the well like that, you can go to much deeper depths than what the typical 25-foot max suction lift is. 100 feet is not out of the way. Back in the day before submersibles came along, um, they had actually had multi-stage, fairly large pumps doing exactly the same thing. And in those cases, they could actually pick up from about 250 feet maximum. Inefficient, but they would do it. Okay. Now, positive displacement pumps, and there's a lot of them. They have several things in common. They are able to handle viscous or thick fluids. They provide reasonably good suction lift capability. They cannot be throttled. Keep that in mind. Water and liquids are not compressible. So always think that a relief valve is needed. They can't be throttled. And most convey a fixed trapped amount of liquid and therefore can be used for metering applications. Accuracy depends upon the internal leakage of the unit uh, and, of course, the controls for it. But basically, they all have that in common. The basic one piston and plunger. You have on the right hand side of this drawing, you have a crankshaft and an eccentric on it, which is moving a connecting rod to a crosshead, goes back and forth, back and forth. When it reteats to the right, liquid is drawn in through a suction check valve. When it goes back, it's discharged up through the discharge check valve. Okay. Pulsation is an issue, so very often they have little shock chambers with air to dampen that, and you can have multiple cylinders to smooth things out a little bit because each one of these has a very distinct pulse. The more cylinders you have, the more it's evened out. Primarily used for high pressure wash, domestic shallow well and sludge pumping applications as well. But the classic one is high pressure wash, like car washes and things like that. Now, going back to history, we had the cistern pump. Now, a cistern pump is like a shallow well jet pump, in as much as typically they were mounted on a counter. As you push down on the handle, it raised that rod. The rod drew water through a check valve at the bottom. This is the first rod through the bottom. And then when it's pushed down, the rod could move down and a check valve didn't disturb it. So basically, you're pumping when you push down on the handle. When you bring the handle back up, it just simply allows the rod to come down. So it's kind of cyclic, but there it is. Now, the next variation on that literally takes that mechanism but moves it way down the well, down a well. And that's your typical, mostly outdoor well pump prior to having motors and whatever. And even with motors, at first they use them to drive these things with an eccentric. And you say the same action. You got a check valve at the bottom and a check valve tied to the rod. When the rod goes down, fluid just comes past that check, nothing happens. But when it comes back up and raises up, the check valve holds and it draws water through the bottom check valve that is stationary. Okay? Diaphragm pumps. Similar kind of action, except you're using a diaphragm connected with an eccentric that goes up and down, up and down. You see them, contractors or the city sometime to clear out ditches or whatever. And again, when it comes down, at the bottom, you can see it on the downstroke. It's pushing liquid to the end, and there's a check valve that keeps it from coming back. Then when it goes back up, liquid is drawn into the chamber under the diaphragm, and away you go. Same kind of act. And they have a surge chamber shown on the inlet side. Very often there's one on the discharge side as well. They can handle all sorts of garbage. They can also be actuated by compressed air by simply having the air pressure on and off of them. Peristaltic pumps, hose pump. As you can see at the top drawing there, basically you have a piece that basically, it's like a toothpaste tube. Liquid comes in at the bottom, the thing is turning counterclockwise, but it's squishing the tube as it goes around, and out it goes. The fluid never touches anything but the hose, so you can get materials that can handle different chemicals. Okay? But hose wear is an issue. In the larger sizes, they actually will oil bath it. If you look at the two drawings below, the one with green, that where they did it so people could see it, actually that would be oil. And as the slider, if you look at the drawing on the right, they've got again these sliding pieces that move up against the hose. It allows them to move fairly smoothly against the hose. Primarily used for handling thick fluids, corrosive, medical heart pumps. This is the way heart pumps are done, peristaltic, or for metering applications. Whether they're the best or not is a matter of discretion. Now, progressive cavity pumps. Has an external helix and an outer stator, which is this stainless thing you can see inside the rubber. and an internal helix on the stator, the rubber piece. Stator has one more helix than the rotor, and when the rotor turns within the stator, cavities are formed which progress from the inlet being to the left of the rubber, where there's actually a shaft coupling, because these things are kind of wobbly and eccentric. They need a shaft coupling that allows some flexibility. That's actually the inlet that discharges to the right. Okay, fine and dandy. Um, Sealing is inherent in the pumps, and the more stages you got, the more pressure you can develop. Again, they've been used for car wash and stuff like that. Um, the elastomer done, but apparently you can actually do them with metal. Um, because of the fact you're steel on elastomer is a fancy word for rubber. We'll get into that later. These pumps cannot run dry for any great length of time. And interestingly, like any valveless positive displacement pump can also play motor. In other words, if you apply pressure at what would be the inlet and discharge the other way, uh, that will actually cause the shaft to turn. And believe it or not, that's how downhole drilling motors operate, okay? Again, used for handling thick and abrasive fluids and can produce very high pressure. The history of this pump is kind of interesting. And I'm going to see if we get, there we go. In 1930, René Moignoux, a pioneer of aviation, while inventing a compressor for jet engines, discovered that this principle could also work as a pumping system. In other words, it was designed as a compressor for jet engines, or I've heard for supercharger for piston engines. Whatever it was, it worked as better as a pump. And he was awarded a doctorate of science for his a new capulism, not capitalism. His pioneering led the ground for progressive cavity pumps. Next, we get into lobe pumps, um, which are very similar to a Roots type supercharger. And basically, the one robe will be rotating one direction, one the other. If it's rotating, the top one would be clockwise and the bottom one counterclockwise. It'll pump from left to right. And you can see basically chambers get caught along, and stuff gets caught along the outside, is pumped through, and then discharged to the right. Um, as the rotors are externally gear synchronized, they're synchronized by gears, they can operate drive for a short period of time, like sludge pumps, used primarily for handling thick or abrasive fluids. I would say they're one of the better pumps for handling sludge. And again, will play motor and thus a power generator suitable for varying flow rates. Interesting thing, it's not uncommon for pumps, centrifugal pumps, to be run backwards, basically to play turbine for generating power. Now, and I remember somebody once said that a distributor, that they had a system that could go right down to zero flows or very low flows. And I thought, I don't think so, because as you already know, centrifugal or kinetic pumps don't like the extremes of a curve. But it turns out they weren't using a kinetic or centrifugal pump. They were using a lobe pump like this, which of course can go down to very low flows because it is a positive displacement pump. Now, there's the name of the company. I don't know where they are now, but if you ever get into something like that, there's a lead. External gear pumps are fairly common. They're like a lobe pump, except they're using a gear. Uh, Classically handling oil and stuff like that. Internal gear pumps, similar idea. The outer part, which has internal teeth on it, is the part that's driven, and the one that they're showing, the smaller gear, is actually an idler. Okay, and again, it creates cavities along the outside that move fluid from the inlet on the left to the discharge on the top. Okay. On a similar vein, we have trochoidal pumps, which are again used for viscous fluids. Um, and they come in different numbers of lobes. And basically, again, they seal a chamber around the outside while things are sealed on at the top of this thing. They're primarily used for engine oil pumps, and the number of those, they can vary. And believe it or not, it's somewhat related to the rotary engine like Mazda uses, which is considered an epitrochoid. Right. Now, moving right along, screw pumps, viscous high pressure pumps, um, where again, similar, although it's a threaded gear that's intermeshing on both sides, by having pumping on both sides, um, the fluid can come from the outside, be forced to the center, which means that the two shafts, the pumps on each shaft, are trying to push out. That's where they're showing the thrust, and the shaft is simply taking the thrust, and that's it. Sliding vane pumps. Again, you have vanes that move in and out as the pressure will tend to force them out. As it turns around, again creating cavities, and the fact that the rotator is off center to the top prevents any backflow. On a similar vein, we have a flexible vane pump, again with chambers on the out. The classic one being, what the heck is it? Anyway, they're used for marine applications, JAPSCO. Um, Marine engines, the water pumps in them are in and outboard motors are inevitably flexible vane pumps. Now, something that is seen in municipal more and more nowadays is the Archimedes screw, which goes back a long time. And as you can see, chambers are formed along the bottom, and as the screw rotates, the fluid will pump up. Very often, in fact, most cases, the thing is only half or less full of water as it moves its way up. And one of the kind of things cool about it is if you're pumping out of a pond, say, to the top, as the level in the pond goes down, it will tend to catch less and less fluid, thereby acting like sort of variable speed. You can control a reasonable level with it. It'll only pump what it's got, sort of thing. The higher the inlet, the more it moves, the more power it takes. And if there's any chance of that inlet being completely flooded, you have to have the reserve power to handle that situation. Okay? Again, they can be used as a generator, a low head generator, and with water at the top flowing down to the right. Okay? Now, with Archimedes screw pumps, there's two variations. The first one is open, as you can see here, which is operating in a trough, and the top of it is actually open. And I've heard of this happening. You can actually watch the ducks go for a ride in the thing as they're moved up to the top. And the lift, of course, is from where it's picking up water to where it's discharging water at the top. They're a big thing for handling fish-bearing drainage or low-lift wastewater. The idea is that the fish can tolerate the fact they're going for pretty much a static ride as this thing turns. Here's a picture a few years back, a SeaWorld in San Diego. Now, there's one of these rides where these rafts start off at the top, a bunch of people in it, goes through a whole big river thing, and then comes back. People get off. The raft is carried up to the top, but the water is pumped up using, in this case, two Archimedes open screw pumps. Why did they do it that way? Because they're fun to watch. They're actually kind of neat to just sit there and see how they do it, okay? Have been used in treatment plants. This is at the James plant in Abbotsford, BC, and has a couple of them that is moving raw sewage up into the treatment plant. Now, you can also have the screw enclosed, which has advantages and disadvantages. There's no inherent leakage. With the previous ones, realizing that screw has a gap between it and the lower channel. And that gap, not uncommon they do them to use a 2x4, so you're talking 1.5 inch gap. And with that kind of gap, there's obviously a lot of leakage coming back. Now, the pressures are low, but still. Now, with an Archimedes screw enclosed, you lose that, so they have no inherent leakage. Hydraulic efficiency is higher, and the enclosing tube, again, I'm going to go back for a second. If you look at these, the bottom bearing on these things is actually on the open one is actually underwater. That means they have to have a pressure system to lubricate that bearing. On the enclosed tube, you can actually have the bearing above water level and have the tube extend down, cantilevered down. Therefore, the bearing is not subject to flooding. Installation costs are lower. You don't have to worry about making the concrete trough, which is what they usually are, and steeper angles are possible. A couple of downsides is if the bottom end gets completely submerged, they can get air in them, and which dramatically affects the pumping capacity. Essentially, you're getting air binding. Also, freezing with pump stationary is a problem. With an open screw, it will drain because of the gap. As soon as the pump stops, it starts to drain back. These don't. Now, one of the advantages of them, you can paint them neat colors. Okay. Something from the past, which you don't see as much nowadays, is the pneumatic ejector, which is more a system than a pump. What it is you have a chamber, and sewage comes in through a check valve into this chamber. Now, when it hits a certain point, the level, it'll hit a level probe. When it does, looking to the right here, we got high pressure air with a pressure regulator and a three-way solenoid valve. That three-way solenoid valve is normally bleeding air off the chamber as it fills up, but when it is energized, it flips and puts high pressure air into the chamber, which pushes down on the liquid, which pushes it up and out the check valve. The inlet inflow check valve closes, of course, and it goes out the other check valve. These things are cyclic. It's not a continuous flow. It can be minutes, maybe even hours, to fill up the chamber, depending on the size of it. And then you have a cycle, and then we go back to it. After a set time of the hit with compressed air, the chamber is vented again, they release the solenoid, and the cycle repeats. Originally was done with a float to open an air valve within the chamber. And at the 1893 Chicago World's Fair, the company Schoen had them for picking sewage up from the various pavilions. Then they went to electronic. They're able to handle debris-laden fluid, but complex and inefficient. When that air pressure dissipates, that's lost efficiency. So efficiency's, back in the 30s, 30%, 40%. But they can handle some pretty rough things, okay? Another very interesting concept is a hydraulic ram pump. Basically what you've got here, let's pretend you have a stream down below and you have a house built at the top of a cliff. The water's down there, you're up there. You'd like to get water, but there's no electricity, so what do we do? Well, what you do is you pull a pipe off the stream and bring it, as you can see down, looking at the left drawing, as that blue line comes down, it flows out, and you notice there's a kind of a weird little valve with a spring on it. And what happens is the flow rate picks up, it starts pushing against that spring, and eventually will slam the spring compressed. That valve will slam shut, and when it does, it creates water hammer. The water then, being pushed by just sheer inertia, will go up through the check valve, and there's an air chamber to kind of dampen it, up the delivery pipe and up to the outlet, which is higher than the stream or anything else down below. As soon as shortly after it's done that, and the pressure shock is dissipated, the spring will push that main valve open again, and the cycle starts again. When you watch these things run, it's kind of a ka-chump, ka-chump, ka-chump action to it. And that's why the air chamber to kind of dampen that out. But, in areas where you have to, particularly overseas, where there is no electricity or whatever, it does pump water. Now that's it for this section, and I do hope you enjoyed.